95% of the universe is made of things we cannot see, cannot touch, and have absolutely no explanation for. Not 5% unknown, 95. And the terrifying part is that the smartest people alive have been working on this for decades and still have nothing. That is where physics stands right now. But to understand how we got here, we have to go all the way back to a street in ancient Greece where one guy looked at a rock and asked a question so simple it sounds dumb. And that one dumb question eventually became the atomic bomb, the GPS in your phone, and a machine that can hear two black holes crash together a billion light years away. This is the entire history of physics. Get comfortable. Picture this. It is around 600 years before anyone even knew what year zero was going to be. You are in ancient Greece. The streets smell like dust and olive oil. People are arguing about politics, about money, about gods. But a small group of people are doing something completely different. They are asking, what is everything made of? Not in a religious way, not which God made it, in a real, physical, observable way. If you take a rock and keep cutting it into smaller and smaller pieces, what do you eventually end up with? Is there a bottom? Is there one thing underneath everything? This sounds simple, but nobody had ever really asked it that way before. The first guy to seriously take a swing at it was a man named Thales. He lived around 600 BCE in a city called Miletus on the coast of what is now Turkey. And his theory was, everything is made of water. Like literally everything. Rocks, air, fire, people. All water in different forms. Was he right? Obviously not. But here's the thing. Thales was not saying Zeus made the world out of water. He was not appealing to mythology or the supernatural. He was looking at the actual physical world and trying to explain it using something he could actually observe. That is the first spark of science. The idea that the world has a structure you can figure out by looking at it carefully, not by asking a priest. After Thales, other thinkers jumped in. Anaximanders said, no, it's not water, it's this undefined infinite stuff he called epeiron. Heraclitus, who was famously difficult and grumpy, said the fundamental thing is not even a substance, it's change. Everything is always changing. You cannot step into the same river twice because the water is always different. Which, when you actually sit with it, is a surprisingly deep observation about the nature of time and reality. But then, around 460 BCE, two men named Leucippus and his student Democritus came up with an idea so far ahead of its time that it still shocks me every time I think about it carefully. They said, if you keep cutting matter into smaller and smaller pieces, you will eventually reach something that cannot be cut anymore. A tiniest possible thing. Totally solid, totally indivisible. The absolute bottom of the ladder of reality. They called these things atoms, from the Greek word atomos, which literally means uncuttable. Everything, they said, is made of these tiny, indestructible pieces moving around in empty space. Different arrangements of atoms make different things. Rocks, water, air, people. Just different configurations of the same basic building blocks. Here's the part that never stops messing with me. These guys were basically right. Not in every detail, but in the core idea. Matter really is made of tiny, indivisible units. Different arrangements really do create all the different things we see. And it would take more than 2,000 years before anyone could prove it. 2,000 years. Democritus had the right basic idea around 460 BCE. The first real experimental proof that atoms exist didn't come until 1905. That's like someone in ancient Rome correctly guessing how smartphones work and then nobody believing them until right now. Now, I need to tell you about Aristotle, because Aristotle is the reason physics was stuck for almost 2,000 years. Aristotle was born in 384 BCE, student of Plato, genuinely one of the most brilliant people who ever lived. He basically founded formal logic. He wrote seriously important works on biology, ethics, politics, metaphysics. He touched almost every field of human thought and left a massive mark on all of them. When it came to physics, he built this whole elaborate system. He said everything is made of 4 elements: earth, air, fire, and water. Each element has a natural place. Earth naturally falls downward because it wants to be at the center of everything. Fire rises because its proper place is near the stars. That's why rocks fall and flames go up. He also said motion requires a constant force. Something has to keep pushing an object to keep it moving. Stop pushing, it stops. When you look at a cart you push along a road, or a boat you row on a river, this seems completely right. Push the cart, it rolls. Stop pushing, it slows down and stops. The problem? Completely wrong. Objects do not need a constant force to keep moving. That's friction doing the stopping, not the absence of force. In a world without friction, an object keeps going forever without anyone pushing it. This is inertia, one of the most important ideas in all of physics. But Aristotle's version matched everyday experience well enough that people believed it for 2,000 years. And then, the Catholic Church incorporated his ideas into their theology, which meant questioning Aristotle was dangerously close to heresy. 2,000 years of wrong physics, not because the evidence was bad, because the institution protected it. But here's something most people skip right past in this part of the story. While Europe was frozen under Aristotle's shadow, something extraordinary was happening in the Islamic world. During the Islamic Golden Age, roughly the 8th to the 13th century, scholars in Baghdad and Cairo and Cordoba were translating ancient Greek texts and then doing something Europe was not: upgrading them, running actual experiments, making actual measurements. One of the most important figures from this period is Ibn al-Haytham, working around the year 1000 CE. He built what we would now call a camera obscura, a dark box with a small hole that projects an image of the outside world onto the wall inside. And from this, he figured out something that sounds obvious today, but was actually a major conceptual shift. Light enters the eye from outside. We see things because light from objects travels to our eyes. Our eyes don't shoot out some kind of vision ray. That is the right answer, and it took a brilliant experimenter with intellectual freedom to arrive there. These scholars kept the fire of scientific inquiry burning during a period when Europe had largely let it go dark. When their work eventually reached European universities in the 12th and 13th centuries, it helped spark what we now call the Renaissance. But the basic framework was still Aristotle. The earth at the center, heavy things fall faster, 4 elements. The overhaul hadn't happened yet. And the question is, what would it take to dislodge 2,000 years of wrong ideas that were propped up by religious authority? The answer starts with a book that one man published right before he died, possibly the most strategically timed publication in the history of science. And the controversy that followed it would get another man put under house arrest for the last 9 years of his life. That story is next. The 1500s, Europe is transforming. The printing press has just been invented and is spreading ideas faster than any institution can control. Artists are painting with new techniques, writers are experimenting with new forms. And a Polish astronomer named Nicolaus Copernicus is quietly working on a book that is going to start a war. In that book, he argued something genuinely shocking for the time. He said the sun, not the Earth, is at the center of our solar system. The Earth is just another planet going around the sun like all the others. The heliocentric model. Now, from our perspective today, this seems obvious. We learn it in elementary school. But put yourself in 1543. The Earth feels completely still. You do not feel it moving. The sun, the moon, the stars, all of them move across the sky every single day. Everything looks exactly like what you would expect if the Earth was stationary and everything else went around it. If the Earth was really spinning and moving through space, why do we not feel it? Why does not everything fly off the surface? Where is the wind from all this motion? These were real, serious questions, and Copernicus did not have complete answers to all of them. But he had the math on his side. The positions of planets made more sense if everything was going around the sun. He published the book in 1543, the year he died. Smart move. Let other people deal with the fallout. There was a lot of fallout. The church was deeply unhappy. This model knocked the Earth and, by extension, all of humanity out of the center of the universe. It messed with the entire picture of the cosmos that Christian theology had built on top of Aristotle's foundations. Now enters Galileo Galilei, born in 1564 in Pisa, Italy. And he is, in the most literal sense, the bridge between the ancient way of doing natural philosophy and the modern way of doing science. The ancient way was think carefully, reason logically, argue eloquently. The new way Galileo championed, test it. Build an experiment, measure things, repeat the measurement. Let the universe tell you whether your theory is right or wrong. Galileo got his hands on a telescope, which had been invented in the Netherlands for looking at ships on the horizon, and pointed it at the sky. What he saw completely wrecked Aristotle's picture of the universe. He saw mountains on the moon. Aristotle had said the celestial bodies were perfect and unchanging, made of that special fifth element ether, untouched by earthly messiness. But the moon had craters and peaks and valleys. It was rocky and rough and scarred, just like Earth. It was a place. He saw 4 moons orbiting Jupiter, 4 objects clearly going around something other than the Earth. If everything in the heavens orbited the Earth, what were these doing around Jupiter? He saw the phases of Venus, which only makes sense if Venus orbits the Sun, not the Earth. He saw sunspots. The perfect, divine, unchanging sun had dark blemishes moving across its face. It rotated. It was a physical object, not a divine lamp. Every single observation crashed directly into Aristotle. One by one, the pillars of his picture of the universe were falling. Galileo also did careful experiments with motion. He rolled balls down inclined planes and timed them with remarkable precision. And he discovered that objects fall at the same rate regardless of their weight. Drop a heavy ball and a light ball from the same height at the same moment, and they hit the ground together. It doesn't matter if one is twice as heavy or 10 times as heavy. They fall together. Aristotle, who had said heavier objects fall faster because they contain more of the earthy element, was simply wrong. He also understood, before anyone gave it a proper name, what we now call inertia. Objects in motion tend to stay in motion unless something stops them. You don't need a constant force to maintain motion, you only need a force to change motion, which is exactly backwards from Aristotle. Here's my honest take on what happened next, because I think it often gets told wrong. The Church eventually had enough. In 1633, the Inquisition brought Galileo in for supporting the heliocentric model. He was forced to publicly recant, to say out loud that the Earth does not move. He spent the rest of his life under house arrest. I used to read about this and think, why did he not fight harder? Why not stand up and refuse? But the more I think about it, the more I think that's the wrong question. Galileo was 70 years old. He was sick. He was alone. The most powerful institution in the Western world was telling him to be quiet. He had already done the work. The observations were real. The measurements were in. No amount of personal bravery was going to change what the data said. Sometimes the most important thing is to survive long enough to make sure the work gets out into the world. And he did. Meanwhile, in Germany, Johannes Kepler was working through the most precise astronomical observations ever made, data collected over decades by the Danish astronomer Tycho Brahe. And Kepler made a discovery that destroyed another assumption everyone had been making for 2,000 years. Planets don't orbit in circles, they orbit in ellipses, slightly squashed circles with the sun not at the center, but at one of the 2 focus points. And Kepler worked out 3 precise mathematical laws describing exactly how planets move. Not vague philosophical descriptions, actual equations, actual numbers, actual predictions that you could check against measurements. This is the moment where you can really feel physics being born as a discipline. Not natural philosophy, physics. Mathematics describing the actual behavior of the physical world, tested against real measurements, making real predictions. Nature follows laws you can write down. And then, in 1642, the year Galileo died, Isaac Newton was born. I want to take a moment here because I think Newton doesn't get the right kind of credit. People know the name, everyone has heard the Apple story, but I'm not sure most people really feel how enormous what he did was. Imagine it's the 1660s, you're 23 years old, there's a plague sweeping through Cambridge, your university shuts down and sends everyone home. You go to your family's farm in Lincolnshire countryside with basically nothing to do for 18 months, except think. And in that time, you invent calculus from scratch because you need a new kind of mathematics for the physics you're working on. You figure out that white light is made of all the colors of the rainbow, and you begin developing the ideas that will eventually become the most powerful scientific framework in history. That's what Newton did during a pandemic, in the countryside, alone, at 23. His key insight about gravity: what if the force that makes objects fall here on Earth is the same force that keeps the moon in orbit? Not a separate, special celestial force for heavenly objects, the same thing. The force that pulls apples off trees is the same force governing the motion of the moon. He worked out the mathematics. The gravitational force between two objects is proportional to both their masses and falls off with the square of the distance between them. Double the distance, the force drops to a quarter. Triple the distance, the force drops to a ninth. And with that one relationship, everything clicked together. Why do apples fall? Gravity. Why does the moon orbit the Earth? Gravity. Why do planets orbit the sun? Gravity. Why do we have ocean tides? The moon's gravity pulling on the water. Why does Earth bulge slightly at the equator? Gravity combined with rotation. One force, everywhere, explaining everything. Then his three laws of motion. Objects in motion stay in motion unless acted on by an outside force. Force equals mass times acceleration. Every action has an equal and opposite reaction. Three laws plus universal gravitation. That's classical mechanics, and for the next 200 years, it was basically all the physics anyone needed. With Newton's laws, you could predict the positions of planets centuries into the future, calculate the exact path of a cannonball, predict solar eclipses to the minute. In 1846, astronomers used Newton's equations to predict the existence and location of a completely unknown planet, Neptune, purely from the way Uranus was wobbling in its orbit. They pointed a telescope at the predicted spot in the sky, and there it was, a planet discovered by math before anyone ever saw it. That's the power Newton handed to the world. Newton published all of this in 1687 in a book called the Principia Mathematica, which is widely considered one of the most important books in the history of human knowledge. It showed that the universe runs on precise, mathematical, universal rules, rules you can write down and use to predict what will happen. But here's the question none of the physicists celebrating Newton in the 1800s were asking. What if the rules have edges? What if Newton's equations only work inside a certain range, and outside that range, something completely different is going on? Something was about to break, and it would start with the most boring-sounding problem imaginable. Why does hot metal glow the wrong color? That question, which almost nobody thought was important, was about to detonate everything. The 1800s were mostly a victory lap for Newton. Brilliant mathematicians developed better tools for applying his framework. Engineers used the new physics to build steam engines, and the Industrial Revolution roared forward. Bridges, railways, machines, all built using Newtonian mechanics, and they worked flawlessly. But two phenomena Newton's framework had not really touched were getting serious scientific attention: electricity and magnetism. People had known about static electricity since ancient times. Rubbing amber with fur makes it attract small objects. Lightning was obviously electrical. Magnets had been used in compasses for centuries. But what were these forces really? How did they work? Were they related to each other? In 1820, while giving a lecture to students, a Danish physicist named Hans Christian Ørsted noticed something strange. He had a wire carrying electrical current near a compass. The compass needle moved when current was flowing. Electricity and magnetism were connected. Moving electric charge creates a magnetic force. This was completely unexpected and immediately important. André-Marie Ampère immediately jumped on this discovery and worked out the mathematical relationship between current and the magnetic fields it creates. Then, Faraday showed the reverse. A changing magnetic field creates electrical current. This is electromagnetic induction, and it is how every electrical generator in the world works today. Whether that generator is in a coal power plant, a nuclear reactor, a wind turbine, or a hydroelectric dam, they all work by spinning magnets near wires. Faraday figured that out in 1831. But Faraday also introduced something conceptually more important than the practical discovery: the idea of fields. Before Faraday, scientists thought about forces as things that acted directly between objects across empty space. Newton's gravity reached from the Earth to the Moon through nothing. This always felt uncomfortable. How does it reach? What is actually doing the reaching? Faraday proposed a different way of thinking. Around every magnet, he said, there are lines of force extending through the surrounding space. The field is a real physical thing that exists everywhere, even where there is no matter. Objects do not interact directly with each other. They interact with the field, and the field carries the force. Fields are real. This turned out to be one of the most important conceptual shifts in the history of physics. Everything in modern physics, every fundamental theory we have, is described in terms of fields. Then, James Clerk Maxwell took Faraday's intuitive field lines and translated them into rigorous mathematics. In the 1860s, he wrote down 4 equations describing all of electricity and magnetism: how electric charges create electric fields, how changing magnetic fields create electric fields, how currents create magnetic fields, how changing electric fields create magnetic fields. 4 equations, complete. One of the most beautiful intellectual achievements in human history. But then Maxwell looked at his own equations and found something extraordinary hiding inside. The equations predicted that oscillating electric and magnetic fields could propagate through space as a wave, an electromagnetic wave. And when he calculated the speed at which these waves would travel, just using the known constants of electricity and magnetism, he got 300,000 kilometers per second, which was the measured speed of light. Maxwell understood immediately. Light is an electromagnetic wave, oscillating electric and magnetic fields propagating through space. And if light is just one kind of electromagnetic wave, there should be others. Waves with longer or shorter wavelengths, traveling at the same speed but oscillating more slowly or quickly. Radio waves, infrared heat radiation, ultraviolet, X-rays, gamma rays. The entire electromagnetic spectrum predicted by 4 equations about electricity and magnetism. In 1887, Heinrich Hertz produced radio waves in a laboratory and detected them. Maxwell confirmed. And from that one experiment in a physics lab in the 1880s, eventually came radio, television, radar, Wi-Fi, cell phones, and every wireless technology that defines modern life. By the end of the 1800s, physics seemed nearly complete. Newton for motion and gravity, Maxwell for electricity and light, thermodynamics for heat and energy, statistical mechanics explaining thermodynamics in terms of atoms and molecules. Some physicists were genuinely saying, mostly joking but not entirely, that physics was basically done. All that was left was to measure things more precisely. They were about to be the most spectacularly wrong that anyone has ever been about anything. There were small experimenting results that did not quite fit. Tiny cracks in the framework. When you heat metal until it glows, classical physics could predict what range of colors and frequencies it should emit. The predictions matched well at low frequencies. But for high frequencies, ultraviolet and beyond, the theory predicted that hot objects should radiate infinite amounts of energy. Obviously they don't. You exist. The world has not been destroyed by infinite radiation from warm objects. This failure was called the ultraviolet catastrophe. Most physicists treated this as a small annoyance, an embarrassing glitch that someone would surely fix soon. The answer to that small annoyance was going to detonate classical physics completely. And the man that accidentally started the demolition didn't even believe what he was doing. His name was Max Planck. He was trying to patch a small hole in the theory. What he accidentally discovered instead was something so strange that he spent years trying to convince himself that it wasn't real. That discovery, and what Einstein did with it 5 years later, is where this story gets genuinely weird. December 14th, 1900, Max Planck gives a talk to the German Physical Society in Berlin. He had found an equation that perfectly fit the experimental data for how hot objects glow. The equation worked, but to derive it mathematically, he had been forced to make an assumption that made absolutely no sense from a classical physics standpoint. He had to assume that energy does not come in a continuous flow. It comes in discrete chunks, packets, quanta. The energy of any electromagnetic radiation comes in multiples of a minimum amount, and that minimum amount depends on the frequency. Higher frequency, bigger chunk. Lower frequency, smaller chunk. The proportionality constant that connects frequency to minimum energy chunk is now called Planck's constant, and it is one of the most fundamental numbers in all of physics. Planck himself did not believe this was physically real. He thought it was a mathematical trick, a fudge factor that happened to give the right answer. He hoped that someone smarter would eventually find a more sensible explanation that did not require this bizarre discreteness. Nobody ever did, because the discreteness is real. 5 years later, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that changed physics forever. Albert Einstein. One of those papers used Planck's quantum idea to explain something called the photoelectric effect. If you shine light on certain metals, electrons get knocked off the surface. Fine, but the detailed behavior was bizarre. The energy of the knocked-off electrons did not depend on how bright the light was. It depended on the color, the frequency. Bright red light could not knock out any electrons at all, no matter how intense you made it. Even a very dim beam of ultraviolet light knocked them out easily. Classical wave physics could not explain this. If light is a wave, as Maxwell showed, then more intense light should deliver more energy and should knock out electrons with more energy. But that is not what happens. Einstein's explanation was radical. What if light actually comes in individual particles? What if a beam of light is a stream of tiny packets of energy, each carrying a fixed amount determined by its frequency? Planck had assumed energy came in chunks when it was emitted. Einstein went further. What if light itself is made of particles? Here is the visual analogy that makes this concrete. Imagine you're trying to knock a bowling pin off a high shelf. You have 2 options. Option 1, throw 1,000 marshmallows at it as fast as you can. Option 2, throw 1 baseball. The marshmallows are light and fluffy. They bounce off harmlessly no matter how many you throw. The baseball is heavy and fast. 1 baseball does the job immediately. Now, the total amount of stuff you threw in option 1 was enormous compared to option 2. But it does not matter. What matters is the energy of each individual impact. That is the photoelectric effect. Low-frequency photons are the marshmallows. High-frequency photons are the baseball. It does not matter how many low-frequency photons you throw at the electron. Each individual photon does not have enough energy to kick the electron loose. 1 high-frequency photon does. This explained the photoelectric effect completely. Einstein got the Nobel Prize for it in 1921. So now, here is the problem. Maxwell showed light is a wave. Einstein showed light is particles. Both are confirmed by experiments. Both are right. Light is somehow both at the same time, which is genuinely philosophically uncomfortable. And then it got more uncomfortable. In 1923, a French physics student named Louis de Broglie asked, if light, which everyone thought was a wave, can behave like particles, what if the reverse is also true? What if particles, like electrons, can behave like waves? Maybe electrons have a wavelength. Maybe matter itself is somehow wave-like. This seemed completely insane. Electrons have mass. They're bits of matter. How can a bit of matter be a wave? When people tested this by firing electrons at two parallel slits, the electrons created an interference pattern behind the slits. Interference, where peaks of waves add together and troughs cancel each other out, is exactly what waves do. Individual particles should just make two bands, but electrons made the striped pattern you get from waves. Particles are waves, waves are particles. What even is reality? In 1925, Werner Heisenberg, 23 years old and suffering from such bad hay fever that he had retreated to a small rocky island off the German coast to get away from the pollen, worked out a complete mathematical framework for quantum mechanics. He called it matrix mechanics. Around the same time, Erwin Schrödinger developed wave mechanics and the famous Schrödinger equation that describes how matter waves evolve over time. The two approaches looked totally different. Different mathematics, different starting assumptions, different physical pictures, but they gave exactly the same predictions for every experiment anyone tried. Eventually, people proved they were mathematically equivalent, two completely different paths into the same room. What Schrödinger's equation describes is called the wave function. It contains all the information about a quantum system, but it does not tell you where a particle is or how fast it is moving or what its energy is. It tells you the probability of finding each possible value when you make a measurement. The universe at the fundamental level is not deterministic. It operates on probabilities. Heisenberg crystallized this into the uncertainty principle. There are pairs of properties, position and momentum being the most famous example, that you cannot simultaneously know with perfect precision. The more precisely you know where something is, the less you can know about how fast it is moving, and vice versa. This is not a limitation of your instruments. This is not because your detector is too clumsy. The universe itself does not have a precise answer to both questions at the same time. Einstein hated this. He spent years trying to find flaws in quantum mechanics, trying to show that the probability was just our ignorance, that there must be a deeper deterministic reality underneath. He and Niels Bohr had this long, famous, deeply serious disagreement that went on for decades. God does not play dice, Einstein said. Bohr reportedly answered, Einstein, stop telling God what to do. Whatever you think about what quantum mechanics means for the nature of reality, the practical predictions are absolutely flawless. It's the most precisely tested theory in the history of science. Every transistor, every laser, every MRI machine, every semiconductor device works because quantum mechanics is right. The GPS in your phone relies on atomic clocks that work on quantum mechanical principles. Quantum mechanics is not some theoretical curiosity. It's running inside every electronic device you own. Nearly a century after it was developed, physicists and philosophers still argue about what quantum mechanics actually means at a deep level. What counts as a measurement? What causes the wave function to collapse from a spread of possibilities to one specific outcome? Is the many worlds interpretation correct, where every possible outcome actually happens in branching parallel universes? These are still genuinely open questions. But while quantum mechanics was being figured out, another revolution was happening in parallel, driven by the same Albert Einstein, and this one was going to completely rewrite your understanding not just of matter, but of space itself, and time itself, and what it even means for two things to happen at the same moment. That story is next, and it starts with a question about light that turns out to have a completely impossible answer. Maxwell's equations described light as a wave traveling at 300,000 kilometers per second, but speed relative to what? If you are running toward a light beam, does it approach you faster? If you are moving away from it, does it come at you more slowly? In 1887, two American physicists, Albert Michelson and Edward Morley, built an extremely sensitive instrument to measure the Earth's speed through the medium that light was supposed to travel through. They pointed it in different directions as the Earth moved through space. No matter what direction they looked, the speed of light came out exactly the same. The medium, called the ether, did not seem to exist. Light had the same speed for everyone. Most physicists were puzzled but did not know what to make of it. Einstein took it completely seriously. He said, what if the speed of light is a genuine fundamental constant of nature? What if it is exactly the same for every observer everywhere, no matter how they are moving? And if that is true, something else has to give, because the standard math of how speeds combine does not work anymore. Here's the analogy I want you to hold in your head, because this one actually makes it click. Imagine two people standing on a train platform. A train passes them at high speed. Someone standing on the train throws a ball toward the front of the train at 20 miles per hour. From the perspective of the people on the platform, the ball is moving at the speed of the train plus 20 miles per hour. Normal physics. Speeds add up. This is exactly what you would expect and experience. Now, replace the ball with a flashlight beam. The person on the train turns it on, shining it forward. The light travels at the speed of light relative to the person on the train. So from the platform, the light should be moving at the speed of light plus the speed of the train, right? Wrong. The light is still moving at exactly the speed of light relative to the people on the platform. It does not matter how fast the train is going. The speed of light is the same for everyone. The only way this can work mathematically is if space and time themselves are not fixed. If a moving clock actually runs slower than a stationary clock. If a moving object is actually shorter in the direction of motion. If two events that happen at the same time for one person do not happen at the same time for someone moving relative to them. Your now and my now are different things if we are moving relative to each other. Time is relative. Space is relative. These are not metaphors or philosophical abstractions. They are experimentally confirmed physical facts. GPS satellites move fast and orbit at high altitude. Both these effects, time running slower because of motion and time running differently because of the weaker gravity at altitude, affect the ticking rate of the atomic clocks on the satellites. Engineers correct for this every single day. If they did not, GPS coordinates would drift by kilometers within minutes. Relativity is not theoretical, it is a daily engineering concern. And from special relativity comes the most famous equation in history, E equals mc squared. Energy equals mass times the speed of light squared. Mass and energy are interchangeable. You can convert one to the other. The speed of light squared is an enormous number, which means a tiny amount of mass corresponds to an enormous amount of energy. The sun converts 4 million tons of mass into pure energy every single second through nuclear fusion in its core. That is E equals mc squared in action. That is why the sun shines and has been shining for 5 billion years without running out of fuel. But Einstein was not done. Special relativity handled objects moving at constant velocity. What about acceleration? What about gravity? Newton's gravitational law said masses attract each other instantaneously across empty space. But if nothing travels faster than light, how can gravity act instantaneously across any distance? Einstein worked on this problem for 8 years, from 1907 to 1915. 8 years of wrong turns, dead ends, published papers he later had to retract, approaches that seemed promising and turned out to go nowhere. It is genuinely one of the most impressive intellectual struggles in human history. The answer he arrived at was so strange, so completely unlike anything anyone had conceived before, that it still feels almost impossible, even though it's one of the most tested theories in physics. General relativity. Gravity is not a force, it is geometry. Mass and energy warp space-time. They curve it. And objects moving through curved space-time follow the curves, taking the geometrically straightest possible path through bent space. What we experience as the force of gravity, what we feel pulling us toward the Earth, is actually us following the shape of the space-time that Earth's mass has curved around itself. Here's the visual metaphor that made this actually click for me. Imagine the universe as a giant rubber sheet stretched perfectly flat and taut. Now place a heavy bowling ball in the middle. The sheet sags under the weight, creating a depression, a bowl-shaped curve around the bowling ball. Now roll a marble across the sheet near the bowling ball. The marble does not travel in a straight line. It follows the curve of the sheet, curving toward the bowling ball, perhaps even spiraling around it. That's gravity, not some invisible force reaching out from the bowling ball and grabbing the marble. The bowling ball changed the shape of the surface the marble is moving through, and the marble is simply following the shape of his world. Now make that four-dimensional with time involved too, and you have general relativity. The Earth does not orbit the Sun because the Sun pulls it. The Earth follows the straightest possible path through the space-time that the Sun's enormous mass has curved around itself. That path happens to be an ellipse. The predictions of general relativity are extraordinary in their precision. Mercury's orbit around the Sun shifts slightly with each loop, a phenomenon Newton's theory could not fully explain. General relativity explained it exactly. Light bends when it passes near a massive object. In 1919, during a solar eclipse, Arthur Eddington measured the positions of stars near the edge of the Sun's disk. Their apparent positions were shifted, exactly as general relativity predicted, because the Sun's gravity was bending the light traveling past it. This observation made Einstein world-famous essentially overnight. General relativity predicts black holes, regions where the curvature of space-time becomes so extreme that nothing can escape from inside a certain radius, not even light. The mathematics said they should exist, but for decades they were treated as mathematical curiosities that probably didn't appear in nature. Then, in 2015, we heard one. Two black holes, each about 30 times the mass of the Sun, had been spiraling toward each other for billions of years. In their final fraction of a second of merging, they released more energy than all the stars in the observable universe combined, all of it as ripples in space-time itself. Gravitational waves spreading outward at the speed of light. When those waves reached Earth, they moved the mirrors in a detector by a distance smaller than 1,000th the diameter of a proton, and we detected it. There's a recording of the signal translated into sound. It's a brief, rising chirp. Two black holes a billion light-years away, and we heard them merge. I find that almost impossible to hold in my head, but it happened, and it has happened dozens of times since. In 2019, the Event Horizon collaboration used telescopes on every continent, coordinated together to act as a single Earth-sized telescope to take the first actual image of a black hole, the supermassive black hole at the center of the galaxy M87, 6.5 billion times the mass of the Sun. You can see the dark shadow of the event horizon, surrounded by the glowing ring of superheated gas. In 2022, they imaged the black hole at the center of our own Milky Way. We can see black holes now. But here's the problem sitting quietly underneath everything we've covered. Quantum mechanics is the best theory of the very small. General relativity is the best theory of the very large and very fast, both confirmed to extraordinary precision. And they don't fit together. Their mathematical structures are fundamentally incompatible. You cannot simply bolt them together. And there are places in the universe where you need them both at the same time. So what happens there? That question is one of the deepest in all of science, and we still don't have the answer. But before we get to the current frontier, there's another whole chapter of the story that happened in parallel. The chapter where physics accidentally gave humanity the most destructive weapons ever made. And it started with a cloudy day in Paris in 1896. In 1895, a German physicist named Wilhelm Röntgen was playing with a cathode ray tube in a darkened room. He had a fluorescent screen across the room that was not connected to anything. It was glowing. Something invisible was coming out of the tube, passing through the air and through the glass, and making the screen glow on the other side of the room. He had no idea what it was. He called them X-rays, the X standing for unknown. They turned out to be high-frequency electromagnetic radiation that can pass through soft tissue but not through bone. The first medical X-ray was of Röntgen's wife's hand. You can see her bones and her wedding ring. She reportedly said after seeing it, "I have seen my death." Doctors could suddenly see inside patients without cutting them open. Medicine changed almost overnight. The following year, a French physicist named Henri Becquerel was investigating whether certain fluorescent materials could produce X-rays when exposed to sunlight. He was working with uranium salts. He wrapped photographic plates in black paper, put uranium on top, and waited for a sunny day to run his experiment. Then it rained, cloudy for days. He put everything in a drawer to wait for sunshine. When he finally developed the plates, expecting nothing because there had been no sunlight, the plates were fully exposed. The uranium had exposed them on its own, in complete darkness, with no external energy source. Uranium was spontaneously emitting radiation. He had accidentally discovered radioactivity. Marie Curie decided to make this the subject of her doctoral research. She found that thorium was also radioactive. Then she noticed something strange. Some uranium ore samples were more radioactive than pure uranium. Something in the ore was even more radioactive than uranium itself. Unknown elements. Marie and her husband Pierre Curie spent years processing literal tons of uranium ore to isolate these unknown elements, boiling down enormous quantities of material in a leaky shed with barely any equipment, extracting tiny amounts of intensely radioactive substances. In 1898, they identified two new elements, polonium, named after Marie's homeland Poland, and radium. Marie Curie won the Nobel Prize in Physics in 1903, then the Nobel Prize in Chemistry in 1911, the only person in history to win Nobel Prizes in two different sciences. She remains one of the most important scientists who ever lived. She died in 1934 from aplastic anemia, almost certainly caused by decades of radiation exposure. Back then, nobody understood how dangerous it was. She carried test tubes of radioactive isotopes in her coat pockets. Her personal notebooks from the 1890s are still so radioactive that they are kept in lead-lined boxes, and researchers who want to read them have to sign liability waivers. She gave her life to the science she discovered, without knowing that is what she was doing. Ernest Rutherford ran one of the most famous experiments in the history of science. In 1909, his team shot alpha particles at an extremely thin sheet of gold foil. Based on the current model of the atom, a diffuse ball of positive charge with electrons embedded in it like raisins in pudding, the alpha particles should mostly pass straight through with minor deflections. Most of them did, but some bounced backward, almost straight back, like they had hit something extremely dense and hard. Rutherford said later it was like firing an artillery shell at tissue paper and having it bounce back and hit you. The only explanation, the positive charge is not spread throughout the atom. It is concentrated in an unimaginably tiny, incredibly dense core, a nucleus. Most of the atom is essentially empty space. The electrons orbit far out from this tiny core. To put this in perspective, if the atom were scaled up to the size of a football stadium, the nucleus would be roughly the size of a marble in the center. The rest is emptiness. You, reading this, are almost entirely empty space. Everything you have ever touched was almost entirely empty space. The discovery of the nucleus opened a whole new set of questions. What holds it together? Protons are all positively charged and should violently repel each other. Yet nuclei with dozens of protons are stable. There must be a force much stronger than electromagnetism at work at very short distances. We now call it the strong nuclear force. And what happens when you deliberately mess with the nucleus? In 1938, two German chemists bombarded uranium with neutrons and found they were producing barium in the products. Barium has roughly half the mass of uranium. Physicist Lise Meitner, who had fled Germany with the rise of the Nazis, realized what was happening. The uranium nucleus was splitting, and she calculated the energy released using Einstein's E equals mc squared. It matched perfectly. Splitting a uranium nucleus releases neutrons. Those neutrons can trigger other uranium nuclei to split, which release more neutrons, which trigger more splits.
a self-sustaining chain reaction releasing enormous energy. This realization came in 1939, the year Europe went to war. The Manhattan Project, the first nuclear reactor under the bleachers of Stagg Field at the University of Chicago in 1942, the Trinity test in New Mexico in July 1945, Hiroshima and Nagasaki in August 1945. The bombs killed somewhere between 130,000 and 226,000 people, most of them civilians. Robert Oppenheimer, watching the first test explosion in New Mexico, recalled the words of the Bhagavad Gita, "Now I am become death, the destroyer of worlds." The scientists who built it had complicated, often haunted feelings about what they had made. The same physics that runs nuclear power plants and MRI machines built the most destructive weapons in human history. Knowledge doesn't decide how it gets used. The people who hold power over it do. After the war, particle accelerators grew bigger and more powerful, and physicists started smashing particles together at higher and higher energies to see what came out. What came out was a mess that nobody expected, a zoo of new particles that made it look like either nature was far more complicated than anyone thought, or there was a simpler pattern hidden underneath that nobody had found yet.
Pions, kaons, lambda particles, sigma particles, delta particles. Dozens of different particles with different masses, different charges, different lifetimes. By the 1950s and 60s, the list had grown so long that physicists started calling it the particle zoo. If all of these were fundamental, nature was appallingly complicated. In 1964, a physicist named Murray Gell-Mann proposed a solution. He said these particles are not fundamental, they are made of smaller things. He called these smaller things quarks, borrowing the word from a line in James Joyce's strange experimental novel Finnegan's Wake. 3 quarks for Muster Mark. A proton is 2 up quarks and 1 down quark. A neutron is 1 up and 2 downs. Other particles are different combinations of quarks and antiquarks. This single idea explained all the patterns in the particle zoo. The dozens of particles were not dozens of fundamentally different things, they were just different arrangements of a small set of more fundamental pieces. But quarks had bizarre properties: fractional electric charge, positive 2/3 or negative 1/3. Everything else in nature has whole number electric charges. And quarks could never be found in isolation. They were always confined inside other particles. Try to pull a quark out and you just create new quark-antiquark pairs from the energy you put in. It's like trying to isolate one end of a rubber band by cutting it. You just get 2 rubber bands. Quarks are permanently confined inside larger particles. The force that holds quarks together is called the strong force, and the theory describing it is quantum chromodynamics. Quarks carry a new kind of charge, called color charge, coming in 3 varieties called red, green, and blue, which have nothing to do with actual colors. The strong force is carried by particles called gluons. At short distances, the strong force is enormously more powerful than electromagnetism. At longer distances, it gets even stronger, like stretching a rubber band, which is why you can never pull a quark free. Meanwhile, 3 physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, showed in the 1960s that the electromagnetic force and the weak nuclear force, which is responsible for certain types of radioactive decay, are actually aspects of a single unified electroweak force at high enough energies. The theory predicted new heavy particles called W and Z bosons that carry the weak force. These were discovered at CERN in 1983. Their masses matched the predictions exactly. By the mid-1970s, all of this had been assembled into what we call the Standard Model of Particle Physics, a complete description of all known fundamental particles and 3 of the 4 fundamental forces: electromagnetic, weak, and strong, not gravity. But the Standard Model had a deep problem. For the mathematics to work correctly, all the force-carrying particles should be massless, but clearly they are not. The W and Z bosons are very heavy, and electrons have mass. So where does mass come from? In 1964, several physicists independently proposed a solution. Add a new field, the Higgs field, that permeates all of space. Every single point in the universe is filled with the Higgs field. As particles move through it, they interact with it, and that interaction is what gives them mass. The more strongly a particle interacts with the Higgs field, the more mass it has. Photons, the particles of light, do not interact with the Higgs field at all, which is why they have no mass and always travel at the speed of light. The Higgs field has a quantum particle associated with it, the Higgs boson, the way the electromagnetic field has photons associated with it. And finding that particle became one of the greatest experimental hunts in the history of science. The Large Hadron Collider at CERN is a circular tunnel 27 kilometers in circumference, buried 100 meters underground near Geneva, Switzerland. It accelerates protons to 99.9999991% of the speed of light in opposite directions and smashes them together. The energies involved are measured in trillions of electron volts. The detectors surrounding the collision point are the most complex scientific instruments ever built, with hundreds of millions of individual sensor channels recording data from 1 billion collisions per second. On July 4, 2012, scientists at CERN announced that they had found a new particle with a mass about 125 times that of a proton and with exactly the properties the Standard Model predicted for the Higgs boson. The last piece was in place. The Standard Model is the most precisely tested theory in the history of science. We can calculate the magnetic behavior of the electron to 10 decimal places, and the measurement matches the prediction. We can predict the rate of obscure particle decays, and they match. The theory works with breathtaking precision. But it is deeply incomplete. The Standard Model does not include gravity. It provides no explanation for dark matter, which makes up 27% of the universe. It can't account for dark energy, which makes up 68%. Together, dark matter and dark energy are 95% of what exists. The most precisely tested theory in the history of science describes only 5% of what exists. The rest is completely outside its scope. So what is the other 95%? That question is where physics is right now. And to understand why it matters so much, we first need to tell you about one of the most humbling discoveries in the history of scientific prediction. The moment we realized that even perfect equations can't always tell you what's going to happen next.
For centuries after Newton, there was an assumption baked into science. The universe is like a giant clock, completely deterministic. If you knew the exact position and velocity of every particle at one moment, you could calculate exactly where everything would be at any future moment. The future was already written. You just needed enough data and enough computing power. Quantum mechanics damaged this at the microscopic level, since the universe is genuinely probabilistic at the quantum scale. But for large everyday objects, classical mechanics still applies, and classical mechanics is deterministic. Surely big things are still predictable. Turns out, no. And the way this was discovered is one of my favorite unexpected stories in all of science because it started with a coffee break. In the early 1960s, a meteorologist at MIT named Edward Lorenz was running weather simulations on one of the early computers. These machines were enormous and slow. A simulation that ran for hours of computer time might model only a few weeks of weather. One day, Lorenz wanted to look at a particular simulation again, but instead of rerunning it from the beginning, to save time, he started it from halfway through, typing in the values from a printout of his previous run. He got coffee, came back, checked the results. The simulation had completely diverged from the original run. After just a few simulated months, the two weather patterns looked completely different, no resemblance. He checked for bugs in the code. Nothing. He checked the equipment. Nothing wrong. Then he realized. When he typed in the starting values, he used the 3 decimal place versions printed on his output sheet. The computer had been running internally with 6 decimal places. The difference was less than 1 part in 1,000, 0.506 instead of 0.506127, a difference smaller than anything a physical measuring instrument could detect. That tiny, unmeasurable difference had grown and grown and grown exponentially until it produced completely different weather. The system was exquisitely sensitive to its starting conditions. Lorenz had discovered what we now call sensitive dependence on initial conditions. In 1972, he gave a talk with the title, "Does the Flap of a Butterfly in Brazil Set Off a Tornado in Texas?" The Butterfly Effect. The atmosphere follows Newton's laws of physics exactly. There is no randomness in the underlying equations, but it is chaotic. Tiny differences in initial conditions grow exponentially over time. This means that even with perfect equations and unlimited computing power, you cannot predict the weather more than about 2 weeks into the future. Not because your models are bad, not because your computers are too slow, because the atmosphere itself is structured this way. It is intrinsically, irreducibly unpredictable beyond that time horizon. Determinism does not mean predictability. This was a genuine philosophical shock to science. We had been assuming these were the same thing since Newton. They are not. Chaos shows up everywhere once you know to look. The double pendulum, just 2 pendulums attached end to end, is chaotic after just a few swings. Dripping faucets can be chaotic. Population dynamics in ecology, the firing of neurons, heart rhythms, traffic flow, the stock market. Complex systems of all kinds exhibit this extreme sensitivity to initial conditions. Benoit Mandelbrot discovered fractals, geometric structures that show self-similarity at all scales. Zoom in on the boundary of the Mandelbrot set and you see endlessly repeating complex patterns, structures within structures within structures, forever. Fractals appear throughout nature, the branching of trees and blood vessels and rivers, the shape of coastlines, the structure of snowflakes, mountain ranges. Nature uses fractal geometry over and over. Chaos theory also gave us important new tools. Instead of trying to predict specific outcomes in detail, you can study the statistical behavior of a system, the overall patterns, the shape of the attractor. Climate is different from weather in exactly this way. We cannot say what the weather will be on a specific day 20 years from now, but we can make meaningful statements about average global temperatures and long-term trends. That distinction matters enormously for how we think about climate change. And chaos forced a kind of intellectual humility onto science. There are inherent limits to prediction that have nothing to do with intelligence or computing power or the quality of your instruments. Some systems are built to be unpredictable in the long run. Accepting that is its own form of scientific progress. Now here is where all of these threads come back together, because cosmology, the science of the universe as a whole, is where quantum mechanics and general relativity and particle physics all collide simultaneously. And what we have found there is both the greatest success story in the history of science and its biggest open wound. The universe, it turns out, is mostly made of things we cannot see, cannot explain, and cannot identify. And that is not a minor footnote. That is the main story.
In the 1920s, Edwin Hubble discovered that distant galaxies are all moving away from us, and the farther away they are, the faster they are receding. Run that movie backward, and everything must have been in the same place at some point in the distant past, the Big Bang. In 1964, 2 physicists at Bell Labs named Arno Penzias and Robert Wilson were calibrating a large radio antenna. They kept picking up a faint, uniform background noise in every direction they pointed it. They thought it might be pigeon droppings inside the antenna causing static. They cleaned out the antenna. The noise remained. They captured and removed the pigeons. The noise remained. It was not pigeon droppings. It was the oldest light in the universe. In the first moments after the Big Bang, the universe was unimaginably hot and dense, too hot for atoms to form. Electrons and nuclei existed as a free plasma. Light could not travel through this plasma because it bounced off charged particles constantly. The universe was opaque, like being inside a fog so thick you cannot see a meter in front of you. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and nuclei to combine into neutral atoms. Light was suddenly free to travel. Those photons have been traveling through expanding space ever since. The expansion has stretched their wavelengths, pushing them from visible light all the way down into the microwave part of the electromagnetic spectrum, and now they fill the sky as microwave radiation coming from every direction with almost perfectly uniform temperature. This is the cosmic microwave background, a photograph of the universe at 380,000 years old, taken simultaneously from every direction in the sky. This background radiation is almost perfectly uniform, same temperature everywhere to about 1 part in 100,000, but there are tiny fluctuations, tiny variations in temperature from one spot to another. Those fluctuations represent slightly denser and less dense regions in the early universe. Over hundreds of millions of years, gravity amplified those differences. Slightly denser regions attracted more matter, became even denser, attracted more. Eventually, after hundreds of millions of years, those tiny fluctuations grew into the first stars, the first galaxies, the filaments and voids and galaxy clusters that make up the large-scale structure of the universe today. The pattern of those tiny fluctuations in the cosmic microwave background tells us the age, geometry, and content of the universe with remarkable precision. The universe is 13.8 billion years old. It is spatially flat, and it is made of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. 95% of the universe is things we cannot directly detect, cannot explain with our best theories, and cannot identify. Dark matter was first inferred in the 1930s by Fritz Zwicky, who noticed that the galaxies in a galaxy cluster were moving far too fast for the visible mass to hold them together gravitationally. They should be flying apart, but they were not. There had to be additional invisible mass providing extra gravitational pull. In the 1970s, Vera Rubin measured the rotation speeds of individual galaxies and found the same problem at smaller scales. Stars at the outer edges of galaxies move much faster than they should based on the visible mass of the galaxy. Something invisible fills and surrounds every galaxy, providing gravitational scaffolding. Dark matter is real. We see its effects everywhere we look in the universe, but we do not know what it is. It does not emit light, it does not absorb light, it does not interact with the electromagnetic force at all. It interacts only via gravity. It is not made of anything in the standard model. Multiple experiments running right now deep underground to shield them from cosmic rays are watching for dark matter particles to collide with ordinary matter. So far, nothing conclusive. Dark energy is stranger still. In 1998, 2 independent teams of astronomers were measuring distant supernovae, using them as distance markers to trace the expansion of the universe over cosmic time. They expected to find the expansion slowing down due to gravity pulling everything back together. Instead, they found the expansion is accelerating apart. The universe is accelerating apart. Something is pushing space apart, not pulling it together. Something that fills all of space uniformly and acts in opposition to gravity. Dark energy. It makes up 68% of the total energy content of the universe, and we genuinely have no idea what it is. When physicists calculate from quantum field theory what the energy density of empty space should be, they get a number that is 120 orders larger than the observed value. That means the theoretical prediction and the measurement disagree by a factor of 1, followed by 120 zeros. It is the worst quantitative prediction in the history of science, and we have no explanation for why dark energy has the small but non-zero value it actually has. There is also something called inflation, one of the most audacious and important ideas in modern cosmology. In 1980, physicist Alan Guth proposed that in the first inconceivably tiny fraction of a second after the Big Bang, specifically around 10 to the minus 35 seconds, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the 26 in an instant so brief it makes no intuitive sense. Before inflation, everything we can now observe was small enough to be in causal contact, small enough for heat and energy to equalize.
Inflation then stretched it to cosmic scales. That's why the cosmic microwave background is so uniform. It started uniform before inflation blew it up to the size of the observable universe. Inflation also explains where the structure of the universe came from. Quantum fluctuations in the field driving inflation got stretched to cosmic scales by the expansion. Those became the density variations in the early universe that eventually grew into galaxies. Quantum fluctuations from the first instant of existence became the large-scale structure of the universe we see today. That's one of the most staggering things I know. And sitting underneath all of this is the fundamental unresolved problem that has defined physics for the last 100 years. We have quantum mechanics for the small. We have general relativity for the large. Both work with extraordinary precision. They fundamentally do not fit together. Where you need both at once, like inside a black hole or at the moment of the Big Bang, the mathematics breaks down. Something is missing, some deeper theory, and we don't know what it is.
String theory is one attempt to find the missing deeper theory. Instead of particles being point-like objects, string theory says the fundamental entities are tiny vibrating strings, many orders of magnitude smaller than anything we can detect. Different modes of vibration correspond to different particles. Gravity falls out of the theory naturally, which is attractive, but the theory requires extra spatial dimensions beyond the three we experience, and it makes predictions at energy scales so extreme we may never be able to test them with any conceivable accelerator. Loop quantum gravity takes a different approach and tries to quantize space-time itself. In this picture, space-time is not smooth and continuous at the smallest scales. It is made of discrete chunks, like how matter is made of atoms. This could resolve the singularities that appear at the center of black holes and at the Big Bang. But this approach also lacks clear, testable predictions with current technology. Both approaches are mathematically sophisticated and genuinely interesting. Neither has yet produced something we can definitively test experimentally. And that is a real problem for physics, because science only moves forward when theories make predictions that experiments can check. Meanwhile, new tools are opening new windows on the universe. Gravitational wave astronomy is barely a decade old. LIGO detected its first gravitational wave event in 2015 and has been detecting them regularly ever since. We have already observed dozens of black hole mergers and neutron star collisions. In 2017, LIGO and Virgo detected two neutron stars merging, and telescopes all over the world observed the light from the same event simultaneously. This confirmed that neutron star mergers are the source of many of the heavy elements in the universe. The gold in your jewelry, the platinum in catalytic converters, the iodine in your thyroid, all forged in neutron star collisions billions of years ago and scattered across space. The Event Horizon Telescope released the first actual image of a black hole in 2019, the supermassive black hole at the center of galaxy M87, 6.5 billion times the mass of our Sun. In 2022, they imaged the black hole at the center of our own Milky Way. We can see black holes now. General relativity's most extreme prediction confirmed visually. The James Webb Space Telescope, launched in 2021, is observing the universe in infrared light and can see the earliest galaxies, formed just a few 100 million years after the Big Bang. Early results are already showing galaxies that are bigger and more mature than our models predicted they should be at such early times. Either the models need adjustment, or something more interesting is going on. Either way, we are learning things we did not know. Quantum computers are being built that exploit quantum superposition and entanglement to perform certain calculations exponentially faster than any classical computer can. We are in the very early days. Current machines are limited and error-prone, but progress is rapid. When large-scale quantum computers arrive, they will be able to simulate quantum systems that are completely beyond classical computational reach, potentially revolutionizing drug discovery, materials science, and our understanding of chemistry. There are also tensions in the current data that may be pointing toward new physics. Different methods of measuring the expansion rate of the universe give answers that do not quite agree with each other. This discrepancy is called the Hubble tension. It might be systematic errors in some of the measurements that nobody has found yet, or it might be a signal that something is genuinely missing from our cosmological model. The most exciting place to be in science is where the measurements do not quite fit. The condensed matter physicists, who study how enormous numbers of particles interact in solid and liquid materials, have spent the last century quietly building most of the technology defining modern civilization. Band theory explained why silicon semiconductors can be made to switch between conducting and not conducting, giving us transistors. The first transistor in 1947 was assembled by hand, roughly the size of your palm. Today, there are more than 10 billion transistors on a chip the size of your thumbnail. Every digital device you own runs on quantum mechanics applied to semiconductor materials. Superconductivity, where certain cooled materials conduct electricity with zero electrical resistance, was discovered in 1911. In 1986, high-temperature superconductors were discovered in ceramic materials that nobody expected and whose mechanism is still not fully understood nearly 40 years later. If we can achieve superconductivity at room temperature and normal pressure, the implications would be enormous. Power transmission with no losses, dramatically more powerful computers, new types of medical scanners, transportation systems using magnetic levitation. We have gone from Thales, saying everything is water, to knowing that everything visible is made of quarks and leptons interacting via force-carrying particles, all of it permeated by a Higgs field that gives particles mass. We have gone from Aristotle saying heavy things fall faster to Newton showing the same force moves apples and planets, to Einstein showing mass curves space-time itself, to LIGO hearing two black holes collide a billion light-years away. We have gone from thinking Earth was the center of everything to knowing we are on a rocky planet orbiting an ordinary star in one of hundreds of billions of galaxies, most of which are being carried away from us faster than light by the expansion of space and will be forever beyond our reach. And the most remarkable thing about all of this is not how much we know, it is what we have learned about how we were wrong. Newton's physics was not wrong, it was right within a certain range. Quantum mechanics was not a replacement for Newton, it was a deeper layer. Each revolution did not erase what came before, it contained it. Classical mechanics still works perfectly for everyday objects. Newtonian gravity still works for most astronomical calculations. What changes is our understanding of where the boundaries are and what lies beyond them. The things we do not know right now are not small technical gaps. Dark matter is 27% of the universe. Dark energy is 68%. We cannot reconcile our two best theories. We do not know what happened at the Big Bang singularity. We do not know why there is something rather than nothing. These are not footnotes. These are the main questions. And the history of physics tells you exactly what happens next. Progress has always come from small anomalies that turned out to be enormous. Black body radiation was a small annoyance that gave us quantum mechanics. The constant speed of light was a puzzling experimental result that gave us relativity. The slight wobble in Mercury's orbit confirmed general relativity. Penzias and Wilson's annoying background radio noise turned out to be the oldest light in the universe. Right now, there are measurements that do not quite fit. The Hubble tension, early galaxies that are bigger than they should be, neutrinos that have mass when the original standard model predicted they should not, the black hole information paradox. One of those anomalies might be the thread that, when pulled, unravels everything and reveals the next deeper layer. Somebody is working on this right now, maybe in a detector deep underground watching for dark matter, maybe staring at data from a space telescope at 2 a.m., maybe writing equations on a whiteboard in an office somewhere, following mathematics toward a conclusion that seems impossible but keeps checking out. Physics is not a completed project. It is the most alive and most open field in human knowledge. Every question we answer opens 3 more. Every theory that works shows us precisely where it breaks down. Reality keeps being stranger than we imagined. From ancient Greece to the Large Hadron Collider,
From atoms as philosophy to atoms as engineering. From watching the sky with naked eyes to listening to it with gravitational wave detectors. The same basic drive underneath all of it, across all of those years, across all of those people. Why? How? What is actually going on? And we are still asking. The story is not over, not even close. If anything, it's just getting interesting. Subscribe so you don't miss what comes next.